So, have you ever stopped to think about how these massive AI models with hundreds of layers actually manage to learn without just breaking? It's a huge hurdle in deep learning, and the clever trick that first solved it is now getting some really fascinating upgrades. Let's get into it. All right, so here's our game plan. We're going to start with the basic shortcut that really made deep learning possible. Then we'll look at why it needed a boost and the kind of unstable superhighway that came next. After that, we'll dive into two brilliant fixes that point to two very different futures for how AI is designed. Okay, first things first, let's talk about the simple yet totally revolutionary idea that let AI models get so incredibly deep and powerful to begin with. You see, the big headache with really deep networks is that as information gets passed from one layer to the next, the signal can just fade away into nothing, or it can explode into total chaos. So how do you keep that signal clean and stable? Well, the answer is a clever little architectural trick that's basically an express lane for information. And that express lane is called the residual connection. It's pretty much the backbone of modern AI like ResNets and transformers. It creates a direct shortcut so data can just bypass layers if it needs to. This is called identity mapping, and it means that even in a crazy deep network, a clean signal can get from the start to the finish without being messed with. And that is absolutely key for keeping the training stable.
So, naturally, researchers saw this simple, one-lane road and started thinking bigger. They thought, hey, what if we built a multi-lane superhighway? We could pump way more information through and make the models even smarter.
And that line of thinking led to something called hyperconnections, or HC. The whole idea was to massively crank up the network's learning power by turning that single stream of information into a whole bunch of parallel streams. This superhighway was supposed to let layers interact in much richer ways, without having to add a ton more heavy computation. And the promise here was huge. This quote really says it all. HOC looked like a brand new way to make AI bigger and better. Instead of just throwing more data or more computing power at the problem, you could actually scale up the internal wiring of the model itself. In theory, it was a fantastic idea. But, theory and reality don't always see eye to eye.
Yeah, because it turns out this awesome new superhighway had a critical, unforeseen flaw. It was built without any guardrails, and, well, things were about to go right off the road.
So here's the absolute heart of the problem. Remember that identity mapping property, the simple rule that made everything stable? Well, by adding all these new uncontrolled connections, HLTC completely broke that rule. Without those guardrails, the signals flying around the superhighway started amplifying like crazy, creating this feedback loop that made the whole training process dangerously unstable.
And how unstable are we talking? Well, in some of the big experiments, the signal got amplified by up to 3,000 times its original value. Just imagine trying to have a conversation where every word you said was 3,000 times louder. It's just chaos. The model's learning process was completely shot.
This visual just nails the issue perfectly. Over on the left, that's a picture of the unstable HC connection. It's a total mess, right? But on the right, that's the solution. Look how clean and structured and stable it is. That's what we're about to dig into. So let's look at the really elegant fix that finally tamed this out-of-control superhighway. It's called Manifold Constrained Hyperconnections, or MHC for short. Now, I know that sounds super complicated, but the idea behind it is actually beautiful. What MHC does is it forces all those chaotic connections to play by a very strict set of mathematical rules. It's like it takes that messy grid and projects it onto a perfectly balanced one. This makes sure information gets mixed and shared properly between lanes, but it never gets amplified or lost. It basically puts the guardrails back on the highway.
This whole process uses a clever algorithm to grab those wild, unconstrained connections and just normalize them. It tames them. And the result is you get the best of both worlds. All the power of a multi-lane information highway, but with the rock-solid stability of that original, simple shortcut.
And the proof is in the pudding, right? I mean, just look at these numbers. Across all these different benchmarks for reasoning, knowledge, and common sense, MHC doesn't just stabilize things, it consistently outperforms both the original model and that unstable HCC version. It's especially good at those tough reasoning tasks.
And here's the real kicker. You get this massive jump in stability and performance for a remarkably low price, just a 6.7% increase in training time. That is an incredible trade-off.
Okay, so MHC perfected the superhighway. It adds capacity and makes everything stable. But, once you've optimized the path the information takes, it naturally leads you to a more radical question about the path itself.
And this question takes us to a completely different kind of architecture, deep delta learning, or DDL.
Instead of just building a better road, DDL asks, what if the road itself could be intelligent?
See, DDL rips out that simple shortcut and puts in something called a delta operator. This thing isn't just a passive pipe for data, it's an active, learnable part of the network. It can actually change its own properties on the fly, deciding layer by layer whether to let information pass straight through, filter it, or even completely invert it.
And it controls this with a single learned value, a little knob called beta. When beta is near 0, it's business as usual. It acts just like a normal shortcut. When it's cranked up to 1, it does a projection. It forgets the old info and replaces it with new stuff. But when it's turned all the way up to 2, it does something truly wild. It reflects the signal, literally flipping it on its head. So this all brings us to a really fascinating crossroads. The ideas behind MHC and DDL represent two very distinct, very powerful philosophies for where we go next in designing AI.
You've got these two incredible paths forward. On one side, you have MHC, which is all about perfecting that superhighway, making it wider, stronger, more robust, so massive amounts of data can flow through reliably. And on the other side, you have DDL, which is like inventing a magical shape-shifting road that can completely change its function depending on what it needs to do.
And that really is the crucial question driving the future of AI architecture. Is the way forward all about perfecting stability at a massive scale, giving us more powerful, predictable models? Or is it about creating these dynamic, flexible systems that have intelligence baked right into their very connections, maybe unlocking capabilities we can't even imagine yet? The answer is going to shape the AIs of tomorrow.